One of the things that you have to be careful about when performing analog to digital conversion or just sampling in general is a concept known as aliasing. And just by way of very brief review, the sampling theorem tells us that in order to completely capture all of the information that exists in an analog signal, we have to sample at a rate that is greater than twice the highest frequency in the signal itself. If we are sampling at less than twice the highest frequency in the signal, then we are doing something called undersampling, and it results in something called aliasing. And essentially what happens is when you undersample, then the information content shows up at the wrong frequencies. And the bottom line is that since there's generally always noise present in continuous time signals, what you have to do is pass the analog signal through a low-pass filter that's known as an anti-aliasing filter that approximately band limits the signal, and then you can with some confidence sample at greater than twice what is approximately the highest frequency in the signal, and then have a good representation digitally. Well, let's take a look at a quick example where we are purposely undersampling the signal and see what happens. So we still have this 5 hertz sinusoid, but now we're going to sample it at 7 hertz, which obviously 7 is less than 10, and so we are undersampling the signal. And let's see what that does. So we get these samples, which, at that's such a low number of samples, it's hard to even tell that this thing is a sinusoid. And if we go ahead and look at the double-sided spectrum, well, remember we're sampling at 7 hertz, so the spectrum can only cover minus 3.5 up to plus 3.5 maximum, and how well it fills that in is a function of capital N. We only have about 7-8 samples here, so it's a very, very crude representation. But here's the main point. We know that the signal started off, the continuous time signal that we were sampling was a 5 hertz sinusoid. But yet, where are our frequencies showing up? Well, about 1 3/4, 2.5 or so is about where the frequencies are showing up. The point is that it's not showing up at 5, and so we're artificially or erroneously seeing frequency content at places where it shouldn't be, and it's because we're sampling at the wrong rate. Now, a more realistic example is that you have a signal that has, say, approximately a 10 hertz component in it, and you're sampling it at greater than 20 hertz, and so you say, hey, I should be in good shape. However, maybe at a somewhat of a low level so that it wasn't obvious, you were actually had a signal that had a strong 10 hertz component in it, but had a weak 15 hertz component in it. Well, if you're sampling at, say, 22 hertz or something like that, well, that's plenty high enough to get the 10 hertz signal, but it's not high enough to get the 15 hertz signal. And what will happen, that 15 hertz signal will show up at something between 0 and 11 hertz if we're sampling at 22 hertz, and you will erroneously think that there is a spectrum, or that there is a frequency component at a place where it doesn't actually exist because you undersample. So anyway, these are one of the cautions that you have to have when you're doing discrete time signal processing, is make sure that you do not undersample.